So, in Chapter 2, we're going to continue our work with describing data, taking a look at location, and taking a look at different types of distributions. So in 2.2, we start off talking about a concept of what's called a linear transformation. Basically, what we can do when we take a look at a distribution, okay, we might want to change all the values in the distribution in such a way that we're potentially, for instance, changing the units. Okay? We might have been measuring something in feet and we want to change it all to inches. Okay? How does that, doing a change in units, okay, for instance, impact all your measurements in a distribution? How does that affect the shape, center, and spread? Specifically, we'll talk about here center and spread. So when we talk about a linear transformation, there's two things that's happening. Okay? We're going to see what happens if we add or subtract some value A. Okay? So we're going to look at adding and subtracting. And then we're going to see what happens if we multiply or divide each data point by some value. How does that impact a distribution? Are there actual patterns that actually occur that could actually save us time than adding a value to every data point and recalculating everything out? So what we're going to do is we're going to do that one time and take a look at what patterns occur. So if you have your calculators out, first thing, or if you don't, take your calculators out, and let's take a minute and just simply enter all this data into list 1. So you can do that right now. I'll pull up my calculator. I believe I actually have it already in my list. So I'll just double check my data points: 25, 23, 20, 17, 14, 12, 11, 9, 8, 7, and 5. Good. I'll give you about 30 seconds to just quickly type those in. So what it then asks us to do is find the 5-number summary, calculate out the mean and the standard deviation. Okay. So as you're finishing up entering in those data points, remember to get all of that information, one variable statistics. So I'm just going to go stat, over to calculate, and I'm going to do one variable statistics on list 1. It defaults already to list 1 for us. So I'm going to start noting some of these key values. So my mean was 13.72 repeating. My standard deviation, S, is about 6.71. Again, I'm rounding a little bit. And then I want to look at my 5-number summary. So I scroll to the bottom. The 5-number summary. I'm just going to write those down here: 5, 8, 12, 20, 25. I am going to throw up one other piece up here, and that's interquartile range, IQR. Interquartile range is Q3 minus Q1, so 20 minus 8 gives me middle 50% range of 12 points, or whatever these values represent. Now, I want to actually see what happens to measurements of center, so my mean and my median. So I want to see what happens to these two values. And I also want to see what happens to my measurements of spread, standard deviation, and IQR when I decide to change all the values. So for instance, in Part B it says, now add 3 units to each data point and find the 5-number summary, the mean, and the standard deviation. Now, I'm going to add 3 rather quickly, and I'm going to use my technology to help me do that quick. Okay? So to do that quickly, all I have to do is go to Stat, go to my Edit, and instead of like going, okay, 8, 10, 11, and so forth, and adding them one by one, I can let my technology do it for me. I highlight L2, and I simply can then just say, second one, which is taking list 1 here, slide this over just a little bit, and add 3. It'll take every data point in list 1 and add 3 to it, so it'll do it all for me all at one time. Nice. Isn't that a nice time saver? So now, let's see what happens to all these measurements. So, we're going to go calculate one variable statistics. I can't hit enter, I have to do it on the list I want. Second 2. So, let's take a look at what has happened now. So when we add 3, our mean is now at 16.72 repeating. My standard deviation is still 6.71. My 5-number summary is 8, 11, 15, 23, and 28. And my IQR, I'll calculate out in just a second. Some of you might be going, well, how in the world did he know that already? Just to show you, as I scroll down, there's my 5-number summary. 8, 11, so 8, 11, 15, 23, and 28. So my median is now 15. My IQR, 23 minus 11 equals 12. So if we were just to kind of take a look at what's happening to my measurements of center? Okay, so they went up by 3. Seems logical. If everybody gets 3 more points or 3 whatever more, should the average and the mean go up by that?
Yes.
Yeah. Right. Like for instance, if I gave everybody extra $5 in here, or an extra 3 test points, shouldn't the class test average all go up by 3 points? Yeah.
Yes, sir.
All right. I should do that more often, right? Now, when we take a look at spread, okay, 2 measurements of spread that we looked at here were standard deviation and IQR. What happens there? No change. Okay? So adding has absolutely no impact on your measurements of spread. And probably the easiest way to see this is looking more at the IQR. Because if you look at the interquartile range, okay, since the Q1 value went up by 3 and the Q3 value went up by 3, it's like all the data points have been shifted up. Okay. Standard deviation and interquartile range is a measurement of spread. So you're looking at basically the lowest score and the highest score, and they're all shifting the same distance. And since they're all shifting the same distance, spread will not change when you add or subtract values to the entire distribution. Okay. All right, let's take a look quickly then at part C. It says now multiply each original data point by 4, find the 5-number summary, the mean, and the standard deviation. So I'm going to do the same thing now, but I'm going to enter it list 3 to equal 4 times list 1. So then I can do one variable stats on list 3. So then I can calculate out the mean and standard deviation and such. So if I go back to my calculator here real quick, stat to edit, I'm going to go over and highlight list 3. I'm going to let it equal list 1 times 4, or 4 times list 1, doesn't matter with multiplication. 2 times 3 is the same as 3 times 2. I get those values. Stat, calculate one variable statistics, Whoops, not on list 1. Ooh, glad I caught myself there. List 3. So, my mean now is 54.90 repeating. My standard deviation, 26.84. My 5-number summary values are 32, 44, 60, but 78, and 112, I think it is. I'll double check that. So I'm just trying to multiply them all in my head real quick.
No.
Yeah, you were a little off.
I was a little off. Oh, I know why I'm way off. Missed parts. You know why I'm way off? I'm multiplying these numbers instead of the original set. So, 20, 32, 48, 80, and 100. That's much better. IQR. Let's see, 80 minus 32 is 48. My goodness. Why am I putting a 6? So, what happens to our mean and our median? Whoa, it gets really big. By how much? Okay. So the center, both measurements are 4 times as big. How about our spread? Did our spread change? It's also 4 times as big. So when we multiply or divide, it actually impacts both. So center and spread change both when you multiply, but only center changes when you're adding or subtracting some value. That is what we have summarized here. So what you can do is, if you memorize those facts, know them, love them, make them your best friend. Make doing linear transformations or calculating out means and standard deviations or medians and IQRs so much easier. It'll save you time and energy. You can still change all the data points, but boy, if you got a lot of them, it takes a long time. Are we okay with linear transformations? Beautiful. Let's go to the next page. Now, what we lead into after linear transformations is what we call density curves. Okay? We've actually been doing a little bit of density curves already in chapter 1 when we try to help ourselves describe the shape of a distribution. Basically, a density curve is just simply a smooth curve drawn over the tops of the bars of your histogram. So if I were to just draw a quick little histogram here, I'll draw one that's skewed to the right here. All a density curve is it's simply a smooth curve drawn over the top of our histogram. Now a density curve has 4 characteristics to it. The first 2 are probably the most important and how we basically show whether or not something is a density curve or not. Okay? First of all, density curves are always above the x-axis. So notice how I stopped at the x-axis. I didn't continue down negative. So all the values are above the x-axis. Our area underneath the density curve is equal to 1. So if this is my density curve, this area underneath will add up to 1, or sometimes we'll refer to as 100% of the scores. The other 2 pieces are basically how we use it. Describes the overall pattern of the data, so it helps us tell us if it's, skewed, right, left, symmetric, etc. And then the last part is how we start to use it even more in this course, and that is the area under the curve between a range of values is the proportion of all observations that fall in that range. Meaning, say for instance, our test scores in this class on the first exam here go from 0 to 100 points. And I want to find out, well, what proportion of students scored between, say, 70 and 90 on the test. What I would be doing is looking at that area in between those two scores. I wrote 99, didn't I? I meant to write 90. Oh, I did, but okay, I see what happened. Okay. So we're going to show you later on in this course how we go about calculating out these areas. Sometimes we'll just use basic geometry. Other times we're going to have to use tables and or calculations on our calculator to find it. Alright, now our density curve also has a couple other characteristics that we want to make sure that you know. The median of the density curve divides the area in half, 50% and 50%. Okay, so 50% of the data points are on the left side, 50% of the data is on the right side. So it divides the area into two equal pieces. The mean of the density curve, however, is the balance point. So you can almost think of it at like a balance scale. So if you start to have outliers or points skewed in one direction over the other, okay, the mean will start to get pulled in that direction. Okay. So if you have symmetric distributions, we talked about this a little bit in chapter 1, okay, the median divides it into areas of 50% and 50%. The mean will be at the same place because if it's truly perfectly symmetric, the left side and the right side are going to be balanced. Okay? But if you start to have a skewed distribution, the mean gets pulled towards the tail of the distribution. So when I see a distribution that's skewed to the right, the mean will most likely be higher than the median, barring outliers, of course. Okay. If it's skewed to the left, the mean's going to be lower. Okay. So that's why when I go back and students will say, well, what was the class average of the test? It's not really an accurate measure because the mean's going to get pulled away from the median. The median would probably be a better description because usually when students are asking what's the average, they're asking for, well, what's the middle score? Where did I do in proportion to the class? So half did above and below, so median tends to be a better representation, especially when you have skewed distribution. Alright, so now, not all density curves are, curved. They can be nice geometric shapes. So here's a quick example where we can find all sorts of different areas and check to see if it actually is. It says, below is the graph of a density curve. Explain why the curve satisfies the two requirements for a density curve. Well, what's the first requirement? Okay, so is our graph above the x-axis? So our graph is above the x-axis. And what's the other thing we need to check? Okay, does the area equal 1? Under the curve. Well, let's just do a check. So what's the base? 2. What's the height? Yeah. So this is definitely a density curve. So we're taking a look at scores that go from 0 to 2 with a height of 0.5 throughout. Okay. So it'd be kind of like what we call a uniform distribution. So it says, what percent of the observations are greater than 1.2? Apologize, and we'll move this up a little bit because I think there's more questions. Oh, did C and D go on the next page?
Yeah.
Did they? Oh, C did. I apologize about that. We'll make that correction. So it says, what part of the observations are greater than 1.2? So this is where you're finding an interval. So what we're doing here is we're going, all right, on my graph, we're looking for 1.2 or greater. So now I'm going to give you some terminology that we're going to write more and more in this class. P stands for, it can stand for probability, proportion, percent. We want to know what, in this case, percent of observations X are greater than 1.2. Well, if I think about calculating this out, okay, some of you could probably just give me the answer straight up, but I'm going to at least show you how I'm getting it. What's the length of the base? 0.8. What's my height? 0.5. So my base length is 0.8. My height is 0.5. Hence my area is 0.4. So, but we want to change it to a percent. It's 40%. I apologize. The next question's on the next page. I'm just going to go to it, then go back. So it says for part C, I'll just write it right here. You want basically the percent, does it say percent? Between, what is it, 0.7 and 1.4? So I want probability that X is between 0.7 and 1.4. So if you're like me, I like to draw pictures, visualize what I'm trying to find. So we're looking at that area right there. So again, my base, 1.4 minus 0.7 would be 0.7 times my height, 0.5, 0.35, or my answer would be 35%. All right, questions so far about density curves, finding the area, their properties, or linear transformations? All right, let's do this.